So, good afternoon, everyone. Welcome to the second afternoon of the European In-Memory Computing Summit, and welcome to my presentation here today. My name is Chris Jenkins. I've been working in the software industry about 36 years now, about 28 of those in the relational database industry, and the last 20 plus years focusing specifically on in-memory database technology. Currently, I work for Oracle Corporation. I'm Senior Director of In-Memory Technology, and I'm the Product Management Lead for the TimesTen In-Memory Database product line. So just to clarify some things and get some things out of the way, because there's often confusion, because Oracle has a lot of different technologies and a lot of different products. Oracle has two primary in-memory database technologies. One of them is called Oracle Database In-Memory Option, and that's an in-memory option that sits inside the big Oracle database and is mainly focused on analytics use cases. And I am not going to be talking at all about that today. I'm going to be talking about my product, which is the Oracle TimesTen In-Memory Database, which is a lightweight, highly available database focused primarily on transactional workloads. And specifically today, I'm going to be telling you a bit about the new 18.1 release of Oracle TimesTen and a major new feature we introduced in that release, which is a horizontal scale-out capability. It's always nice to start with a little bit of history. So TimesTen was born in 1996 outside of Oracle. And we were a separate independent software company, and we released our product to market in 1998, and at that time it was the world's first commercial relational in-memory database. And even at that time, we already had, or very shortly after, replication for high availability, online upgrade capability. A year or so after that, we introduced the first iteration of our functionality to be able to cache data from an Oracle database into TimesTen to improve performance, even though we weren't part of Oracle at the time. And I joined the company in 1999, round about there. Okay. In 2005, we were acquired by Oracle, so actually now the biggest part of our history has actually been inside Oracle. And over that time, we've added all sorts of new features and functionality to the product, many of which are, stealing technology from the big Oracle database and putting it into TimesTen, because why wouldn't we do that? And all the time, improving performance, scalability, reliability, and availability. So I think, the big takeaway here, first of all, is that this is a very mature product. The code base has been around a long time. It's had a huge amount of customer exposure. Okay. Today, we're going to be focusing on 2018, the 18.1 release and the major new feature of TimesTen Scaleout. And I'm pleased to say that we are now GA. We went GA with the 18.1 release in May. So it's been out now for just about a month. Okay. You may not realize it, but we have thousands of customers deploying TimesTen around the world. Some of these are end-user customers who have bought TimesTen from Oracle for use in-house developments, but a lot of them use ISV or OEM applications that they've purchased from another vendor, which happens to have TimesTen inside it. And in many cases, they may not even realize that they're using TimesTen. So before we get fully into scale out, I want to just explain some changes in the 18.1 release around deployment options and how you can deploy TimesTen. So traditionally, all the way from inception up until now, you've been able to deploy TimesTen in two main ways. The first way is either as a standalone in-memory database, so your application will store whatever data it wants in the database and use it as essentially the system of record, with full persistence, full recoverability, everything else. And very commonly, you will use TimesTen replication to make that system highly available. In fact, probably 80+%, maybe 90% of our deployments typically are high availability configurations with replication. And that kind of configuration, the application is typically one that requires low consistent latency for database operations and or very high throughput. And it's very common to find us used in, as I said, ISV or OEM scenarios where we're actually integrated inside some other application. The second way of using TimesTen traditionally has been as a cache for the Oracle database. You can deploy one or more TimesTen databases in front of your Oracle database, and TimesTen has rich built-in functionality that lets you define a subset of the tables and the data in the tables from Oracle, pull it forward into the TimesTen cache, and then maintain synchronization as data changes in either location. Applications can access the TimesTen cache and obviously get better response time and potentially higher throughput than if they went direct to the Oracle database. So those have been available pretty much since day one of TimesTen, but now in the 18.1 release, we are rebranding those two deployment options under the name TimesTen Classic. Okay? And when you deploy TimesTen like this, you're typically looking at, in the best case, microsecond level response times for SQL operations, and depending on your hardware and workload, up to the millions of TPS throughput on a single commodity server. That's the kind of performance envelope for that. Today, I'm going to introduce and completely focus on a brand new deployment model or option in the TimesTen 18.1 release called TimesTen Scaleout. And for this, we have evolved the core TimesTen product to become a distributed, shared nothing relational in-memory database. Basically, we've added a horizontal scaling capability here. Okay, so this brings with it now much higher throughput and storage capacity because we're not limited any longer to the hardware capacity of a single machine. It has transparent data distribution, elastic scalability, and it's fault tolerant, and I'm going to be talking a lot more about those areas as we go through this session. And when deployed in this kind of configuration, potentially you can reach hundreds of millions of TPS throughput or billions of queries per second, again, subject to hardware and all the other things. Okay? So what are the benefits of TimesTen Scaleout, particularly compared to regular TimesTen? Well, I've just said it's fast and it's scalable. It offers low latency and high throughput. TimesTen has always been very vertically scalable. We can do very well on a single machine as you increase the size of the memory and add processor cores. So our vertical scalability across several recent releases has been really good. But now with this, we also have horizontal scalability. So you can scale in 2 dimensions now. The system has been designed from the ground up to avoid any single point of failure. It's fully persistent. It provides high availability through the use of K-safety. And all the database elements are active for both reads and writes, so it maximizes the utilization of the hardware. It provides a single database image to applications. So as you'll see in a minute, although the database is physically sharded or distributed, and you won't hear us really use the word shard, we don't like to use that word, logically, the application sees a single logical database and is totally unaware of the fact that it's a distributed database, which is what we mean by data location transparency. The application can connect to any element that's part of the database, and it can then issue queries and transactions that span the entire database without regard to where the data is physically located within the grid. And lastly, but certainly not least, TimesTen Scaleout is very easy to develop applications for. We support a wide range of languages and APIs. We're very compatible with the Oracle database in terms of data type SQL. We have PL SQL. And it's also very easy to deploy and manage because one of the key things we built into the system as we developed it was to facilitate a single place where you perform all your installation, configuration, patching, management, monitoring, rather than having to deal with 70, 80 different systems and having to log into each one. And we'll dive into a lot of this in more detail as we go on. So I've already used the term database element a couple of times, so let's clarify what I'm talking about when I talk about that. So in the big picture, we have a database that's made up of lots of database elements distributed across a whole set of either physical hosts or virtual machines or containers, whatever you like, okay? And typically, each machine will host one database element. Doesn't have to be that way, but that's the usual deployment model. And each of those database elements will store a portion of the total database data, okay? If you look more closely at each of those elements, you will see that they actually look very much like a TimesTen classic database. There's a block of shared memory, which is the actual database, the operational database, and then we have the persistence mechanism on local storage. Remember, this is a shared nothing system, and that's where we keep the checkpoint files and the transactions log to provide local persistence for the database, okay? So basically, any TimesTen Scaleout database is built up from a set of elements working together. And they are the smallest unit for persistence, recovery, availability, etc. So that's a physical look, okay? Thinking about it logically, if you look at an element from a logical perspective, every element in the database contains the entire metadata for the database. It has all the information about all the users of the database, all the database objects, tables, indexes, views, whatever. They all have the full picture. And they will each contain some rows for each table in the database, okay? So they have all the metadata and some of the data, which leads naturally to the question, so how is the data distributed across the elements in a TimesTen Scaleout database? That's something you choose as part of building your data model and defining your data model. You choose one of the available distribution methods for each table you create. And in the initial release, we have 3, but we certainly plan to add additional distribution methods in future releases. So at a high level, the 3 options you have are distribute, spread the rows across the elements. Co-locate, if you have parent-child relationships, you can co-locate the child rows with the parent rows. That's a performance optimization. And duplicate, if you have intensively read tables, particularly if they're relatively small, like lookup tables or reference data, you can actually store a full table copy everywhere to make all access to that table local in every element. Now, let's just look a little bit more detail at these different distribution methods. So hash, this is the most general purpose distribution method and is probably the one people will use most, okay? When you distribute a table by hash, you will optionally define the set of columns you want to use as the distribution key. If you don't define it, we'll default to using the primary key. And if there isn't a primary key, we will synthesize an internal key for this, okay? When a row gets inserted into the database, we will perform a hash on the values for the distribution key, and that will determine which element in the database that row will be stored in. That also allows us later on to locate that row if you do a query that happens to use the distribution key, for example, okay? And this generally results in a reasonably even distribution of data across all the elements in the database, okay? And you can see a little example of how you might define that down the bottom there. There's nothing explicitly specified, so it will use the primary key columns as the distribution key. Distribute by reference, this is how you co-locate child rows with their parents. So obviously in relational databases, it's very, very common to have parent-child relationships, of course. You can see here at the SQL level, the DDL level, we have the customer table with the primary key, and then the orders table, which stores orders related to customers. And here we have the customer ID, which relates back to the customer's table, defined as a foreign key constraint. And here we can distribute by reference using that foreign key constraint. And what that means simplistically is that for any given customer, all the order rows that belong to that customer will be physically stored in the same database element as the parent row. And depending on your workload and the kind of queries you're running, this can be a really good performance optimization because it means that joins and potentially transactions will tend to be local instead of distributed. And the less network round trips there are, the better, okay? And you can do multiple levels of this. You're not limited to one level. You can have 2, 3, 4 levels of reference depending on the depth of your table hierarchy. And then lastly, as I mentioned, we also have this duplicate option where you can store a full table copy everywhere. Clearly for this distribution method. Updates are relatively expensive, but reads are really good because all reads are local. If you join against this table, it's always a local operation. Okay? So those are your choices in the first release, and in future releases we will add things like range-based distributions and stuff like that. Let's take a little look about high availability now. So we have built-in automatic high availability by way of something called K-safety, and that simply means we maintain multiple copies of the data within the database in different physical elements to provide availability in the event of some kind of failure. Okay? Obviously, the database automatically keeps all those copies in sync. So we typically draw a scale-out grid or scale-out database using a diagram or picture like this, where we have the elements labeled here. You can see we have A and A prime. They are copies of each other. B and B prime, they're copies of each other. But actually, in terms of how you actually configure the system and how you monitor it and everything, it's better to think of this more like this. And this introduces some of our terminology as well, okay? So you can see that A and A prime, which are replicas of each other, form what we call a replica set. No surprise there, right? Similarly, we have B and B prime, that's replica set 2, and so on. We also have this notion of a data space group. So A, B, C, and D form one complete copy of the entire database. And that's a data space group. And then A prime, B prime, C prime, and D prime are a second copy. And if we had K greater than 2, we'd have a third copy, and so on and so forth. Okay? So replica set and data space group are kind of orthogonal to each other. And that's more the real topology of the system, if you like, and how you will see many things presented to you when you're working with the system. Okay? All of these replicas are active for reads and writes. So an application can connect to A and to A prime, and it can issue both queries and DML and transactions. There's no master slave here. It's all active everywhere. And that's good because that increases your compute capacity. It allows you to leverage, the power of all the hardware for all kinds of operations. Okay? As I said, you can initiate transactions everywhere, and the queries and transactions, they can span all these elements because they just see one big logical database. They're unaware of this lower level distribution. How does this provide fault tolerance? Well, I guess that's kind of fairly obvious, I hope. Failures will happen. And in large distributed systems, failures are actually the norm. If you've got a 64-node system, at any given time, it's very likely that some system somewhere will have a problem, right? And if you have 128, it's even more likely that something somewhere will have a problem. We can tolerate lots of failures as long as you have at least one element in each replica set up. The database continues to function. Applications don't even realize anything's gone wrong. Okay? Things continue to run for both reads and writes. If you're using client-server connectivity and you were connected to one of the failed elements, then the connection will fail over to one of the surviving elements. Okay? So providing there's one copy of the database, everything just carries on. And that's kind of nice. Generally speaking, these failed elements will recover automatically. So if the system has crashed, when it reboots, TimesTen gets restarted, we'll recover the element from the local persistence copy first, and then we will resync using log-based catch-up and or duplicate from one of the peers in the replica set. When everything's resynced, the element rejoins as a full member of the grid, and that all happens automatically. Okay? Similarly, if there's a software failure, providing the TimesTen processes are still running or have been restarted, the same thing will happen. So in most failure scenarios, not all, you don't have to do anything manually. Sometimes you may have to intervene and run some commands, but most failures will tend to recover automatically. Now, what happens if you're very unlucky and all of the elements in one of the replica sets fail at the same time or are down at the same time? Clearly, that data is not available currently until that replica set is recovered. Okay? So the default behavior here is that other transactions and queries will continue, provided they don't depend on any data here. If they do, you'll get an error saying, sorry, can't complete that request, replica set 4 is down. That's pretty much what the error says, actually. Now, for some types of application, it's more important to get an answer than necessarily getting the exact correct answer. So by explicit application request, we will allow an application to receive a partial result. If it says, I want to run this query and I accept that some of the data is not available, we will give it back. We'll run the query on what data is available and give it an answer. But that application has to explicitly ask us for that, because that's not really the right answer, right? A little bit about scalability. So this is all great so far, but what if I want to grow my database, or maybe shrink my database to accommodate, more or less capacity? So TimesTen Scaleout provides an elastic scalability capability. You can dynamically add or take away elements in multiples of replica sets, and then you can redistribute the data to those elements or away from those elements to change the size of your database, which results in an increased or decreased storage capacity and an increased or decreased compute capacity. It's a two-step process currently. So say here we have what we would call a 4x2 database, right? So it's 4 replica sets with k factor 2. And so we want to turn this into a 5x2 database. We want to add an extra replica set. We would execute some management commands on the management location. It would take actually 3 commands to do this. Okay? And what would happen when we complete those commands and say go, under the covers, we would configure the new 2 hosts. We would install the software remotely on them. We would configure the TimesTen installations. We would spin up the TimesTen instances and create the database elements all automatically for you, so that they were then ready to start hosting data. Now, up to this point, there's been absolutely no impact whatsoever on the database, because we're just spinning up new capacity. We haven't done anything to bring it into use yet. If you wanted to add multiple replica sets, you could do them all here and get them all ready. When you're then ready to bring them into use, you execute another command that basically says, redistribute the data. And we will then move the minimum amount of data necessary. Remember, it's consistent hash, so we don't have to redistribute everything to achieve a new even distribution that includes the additional replica sets. And then they will come into play. They will start participating in queries and transactions. New client-server connections will be preferentially routed to those elements, because they will start off with no connections. So the load balancing will tend to fill them up first as new connections arrive until connections are more even. I mentioned a few times that we have a single point for installation, configuration, management, and everything else. And this is really a very important feature. If you have a large distributed environment, 50, 60, 70 nodes, you can imagine these things can get quite unmanageable, right? You've got all these different machines, what's the configuration, what are they doing, what are they running on? Do I have to install the software on everywhere? No, you don't, okay? There's a single place where you do everything, and we take care of all that under the covers. So installation, patching, configuration, database operations, backup, restore, all that kind of stuff. You can perform your management operations and your monitoring in 2 ways. We have a command line interface, so there's a couple of command line tools. And that's obviously ideal if you want to script things and do other stuff like that. But if you prefer a more GUI kind of console, then the Oracle SQL Developer GUI tool has very deep and rich TimesTen support, both at the database level in terms of manipulating tables, running queries, and doing all that kind of databasey stuff, but also around managing a TimesTen grid. And here's a couple of screenshots of the kinds of stuff. So you can actually do about 97% of operations that you can perform on the command line through SQL Developer, so it's very comprehensive. I think there might be 1 or 2 things you can't do with SQL Developer, but pretty much everything works with SQL Developer. And you can mix and match those. It's not a case of one or the other. You can do some things on the command line, some things through SQL Developer, whichever you prefer. And as you may be aware, SQL Developer is free. It's not you don't have to pay anything to use that. It's just a free download. Okay, I wanted to include this. So this is the big architecture picture. This really shows a production TimesTen Scaleout deployment. And I just want to call out a few things in here just to give you kind of the big picture, okay? So this is the guts of the operation. Here we have all the data hosts with the data instances. So we have a k=2 system. It's a production system, so clearly we want high availability. So this is a 4x2 database here, and that's where all your data resides. Okay? Here is the management point. We call it a management instance, and that's a very small, specialized TimesTen instance deployed on a separate machine, typically. That's best practice. And that's where you perform your management operations. And in a production environment, we generally recommend that you configure that as a HA pair. That's, again, it's automated. You just tell us you want a HA pair, and that's what you get. The reason being, this thing doesn't actually participate in queries or transactions. So even if the management instance goes down, these things all carry on and the applications continue running, but you can't do any management operations. And if something bad happens over here while that's down, you are limited in your ability to fix it. So by having a HA pair, you know, if the primary fails or you have to take it down for maintenance, you can simply promote the standby to active and do your management there. Okay? Any kind of distributed system requires some kind of quorum or membership service or something to figure out, you know, who's up, who's down, who can talk to each other, who can't talk to each other. So we use for that a third-party open source product called Zookeeper. This is very, very prevalent in the industry, used by lots of different things for this and other uses. We make fairly limited use of Zookeeper. Our use of it is fairly lightweight, but it is a critical component of the architecture, at least at the moment. We provide Zookeeper distribution as part of our download, and we provide instructions and a documentation for installing and configuring it. It's really very simple. It takes about 5 minutes. Okay? In a test and dev environment, you can get away with one Zookeeper server, but for production, again, you really need at least 3, and for, you know, a large grid, we probably recommend 5 Zookeeper servers. Okay? Another component that you would probably configure is what we call a repository. It's like a bit bucket. It's a storage area. Okay? It's used for things like database backups. It's used for things like database export. It's used for gathering diagnostics. So you typically will want at least one of these in a production grid. You can have more than one, but you typically want at least one. And that system, it's just another machine with some storage, the file systems that you want to make available as a repository. And it can either be mounted using something like NFS across all the data instances, or if you don't have NFS, they can actually access it through SCP. And that's all part of the grid configuration as well. Okay? All of these things are connected together using what we call the internal network. So this is the grid interconnect, if you will. It's a really important piece of the puzzle. Okay? This network needs to be fast, high bandwidth, low latency, and secure. Okay? Kind of goes without saying, but yeah. Okay? And all the management stuff within the grid is done using key-based SSH. So when you execute command on the management instance, under the covers, it will use key-based SSH to these things to execute various commands on those. Okay? So part of setting this all up is to establish trust amongst all the systems. Outside of the database, obviously the whole point of a database is to support applications, right? I mean, who has a database without applications? No point, right? So the applications kind of typically maybe set out here, maybe some of your tools as well, and they will connect to the database using a second network, which is the externally facing network, okay? So for example, if this was a cloud deployment, all of this would sit in the cloud, and then that would access it potentially either from a different area within the cloud through, you know, into cloud networking, or potentially across the internet from outside, depending on, you know, the kind of application you're doing here. Okay, makes sense? Right, I want to talk now a little bit about performance. We're getting towards the end, actually. This is moving along pretty well here. So the first thing I want to introduce, because it is kind of important, is how do applications connect to and interact with a TimesTen database. And this isn't specific to Scaleout. This also applies to TimesTen Classic, and it's been like this since the product first began. TimesTen supports 2 different types of application connectivity. And these 2 different types of connectivity are supported by all the APIs that we provide, okay? So regardless of the API you use, you can choose one or other. The first one we call direct mode. For direct mode, the application processes have to run on the same physical host or inside the same VM or inside the same container as either the TimesTen database, if it's a classic database, or one of the TimesTen Scaleout elements if it's a Scaleout database, okay? And when the application opens a connection to the database using JDBC or ODBC or OCI or whatever you're using, ODP.NET, whatever, okay? Under the covers, through the TimesTen engine, which is linked as a library with the application, we attach the shared memory segment and map it into the local process address space. So from that point onwards, SQL interaction with the database is essentially in-memory function calls and local process in-memory data access. No IPC, no context switch, no network, no nothing. Why is this good? For all those reasons. This gives you very, very low latency between the application and the local database or local database element. Okay. The other connectivity option we support is essentially classic client-server. Okay. So when you run this mode, you will have one or more server processes configured to run locally for the database, each of the database elements, and then your applications will run somewhere else, and there will be a network connection, TCP/IP, where the applications can connect to one of the servers. They can send requests, the server executes the request, sends the answer back to the application. And those servers are essentially specialized direct mode applications. Okay? They're multi-threaded, try and reduce the process overhead and context switch overhead here. Obviously, a lot of applications may have to run like this, but it's important to understand, you know, every database interaction here involves at least one network round trip, maybe more. And there is, you know, potentially more context switching and other stuff going on here. So, you know, it's choices, right? You can use one or other or both. So you're not limited to doing it all one way or all the other way. You can mix and match depending on requirements. And many customers may have, you know, some application components that run locally in direct mode and other things that run remotely over client server. Why was I talking about that? Well, because I want to introduce now a little bit about how can I control and adjust and improve and optimize the performance of my TimesTen Scaleout database. Now, this is a very big topic. I could easily do a 3-hour presentation just on this topic alone, and we only have, you know, a very limited time today. So I'm just going to touch on the different factors and talk a little bit about each one, but I'm clearly not going to go into huge depth on these. Let's start with the network. We're talking about a distributed system. When an application sends a request into the Scaleout database, we're going to figure out how to execute it. It may turn out that all the data we need is in the local database element. That's the best possible case. But in general, it won't be. Some data may be elsewhere. The query may do a select count star from a huge table. We may have to touch every element. So there will be internal grid traffic that has to occur across the internal network to satisfy SQL requests. And the more traffic there is, the slower things will tend to go, because the network typically is much slower than memory access, obviously, right? So the performance of your network, and especially the latency of the network, is really critical. And, you know, our experience suggests that for production, you certainly want 10 gig Ethernet as a minimum, okay? Depending on your workload. But, you know, you can run it on 1 gigabit Ethernet, but you're not going to get fabulous performance, right? It's an obvious statement, but, you know, the processing power and RAM capacity of the individual hosts that host the database elements is obviously important, okay? You know, the more CPU you have, the more RAM you have, the more data you can store, the more processing you can perform on each of the database elements. And that kind of ties into the next 2 points. So these 3 points are kind of related, okay? Another factor to consider is how many physical machines or virtual machines am I going to use for my database grid? And how many scale-out instances am I going to configure? Generally, you will run one scale-out instance per machine or per VM, but again, that's not a hard and fast rule. You can have a very large machine and you can actually run multiple separate scale-out instances on it, okay? The reason this stuff is all important is because of the network, okay? if your objective is absolute best performance, you actually want to veer in the direction of a smaller number of larger nodes rather than a lot of very small nodes. If you think about it, for a given amount of data and a given workload, if I have a 4-node system versus a 16-node system, there will be 1/4 of the internal network traffic for the same workload and the same amount of data. It'll go faster. Okay? So these are just factors that you need to bear in mind and do some experimentation with as part of building your configuration. The way you choose to distribute those tables, whether you use hash or reference or duplicate, and the choice of distribution keys will have a big effect on your performance. Okay? And frankly, to choose these properly, you need a knowledge of the workload. Now, the good news is we are already working on a distribution advisor. It's not available yet, but it will be coming in a future release, whereby you will be able to run a workload, and we will spit out a whole bunch of recommendations saying you should distribute this table like this and this table like this. So it's not there yet, but it's in plan. Okay? Right now, you have to kind of think about it a bit yourself. And obviously, you can call on us for assistance. It's a relational database. Indexes are very important. Okay? That's the traditional way to optimize data access, particularly queries in a relational database. Even more so now in Scaleout. We actually have 2 different sorts of index. So we have local indexes, which are wholly contained in each individual element. So once you get to an element, if you're using a key that matches the index, we can find a particular row in that element very quickly, but you've still got to figure out which element you need to go to. And for some kinds of operation, that might require a broadcast to all elements or to some subset of elements. So local indexes will speed up data access to some degree, but as with all indexes, they will slow down DML, inserts, updates, and deletes, because typically they require you to maintain the index. Nothing's free, right? This is standard database stuff. We also have global indexes. So they are global, not local, okay? So they will give you much faster data access because they combine the which element do I need to go to with where in the element is the data. But of course, the maintenance of these is also global and is therefore heavier impact on DML, of course. Okay. So those are all things you can do around hardware, data models, schema, and all that kind of stuff, right? The last thing, but again, by no means least, is the application. Now, I'm sure I don't need to tell you guys, right? You can have the most fabulous database in the world running on the best hardware, and you can super tune it, and then you take a terrible application and put it on top of that database, and what will happen? The performance will suck big time, okay? You cannot fix bad applications by tuning your database. I mean, you can mitigate them maybe to a little bit, but you can't fix them. So, as with all things, you need proper design, proper implementation. You want to choose the right connectivity mode, direct versus client server. And these are really, some of these choices are architectural choices, not just implementation choices. Okay. Now, another important point to note here. I said a few times earlier in my talk today that we present a single logical image to the application. We have data location transparency, and the application doesn't need to care where the data is, right? But for certain types of application and certain types of workload, if the application does know where the data is, it can gain a big performance boost. So we have APIs that will expose that information if applications wish to use it. And if you use those APIs and you have the right kind of application, you take the trouble to implement the use of these APIs in the application, then the application can basically go to the element where the data is instead of having to go into the grid over here and then have internal communication. So for certain applications and certain kinds of workloads, that can provide a significant performance boost because it reduces or even eliminates internal grid round trips. So having said all of that, I just wanted to give you some benchmark numbers. Benchmarks are benchmarks are benchmarks, right? But if I didn't put any numbers up, everyone would say, well, he didn't show us any performance numbers. So let's talk a little bit about this, because the details are always important, all right? So this benchmark is an OLTP workload called TPTBM. It's a very simplistic little benchmark, and we've been shipping this benchmark as part of the TimesTen product since the beginning of time, okay? It does key-based operations, either select a single row, update a row identified by a key, insert a row, or delete a row identified by a key, okay? So for this benchmark, we ran it with a mixed workload, 80% select, 20% update. We ran it in direct mode, so the application processes are running on the same nodes as the scale-out data elements, okay? So there's no client-server traffic here. We enhanced this benchmark to implement locality optimization, so we can guarantee that data access is always local. So our application process running on host 1, connected to element 1, all its data access happens in element 1. So the internal network round trips are for the K safety. This is a K equals 2 system, okay? We ran it on pretty good hardware. So we've used the Oracle bare metal cloud, of course, 64 BM high systems. So they're Oracle Linux 64-bit, Xeon 2.3 gigahertz, 10 gig Ethernet, and NVMe flash storage, okay? And I'm trying to remember, I think these are 22 cores per system, if I remember rightly. And what we did basically was we started off with 2 nodes, and we added more and more application process till we reached peak throughput. Then we added more nodes with application processes, and again, we ramped them up until we reached peak throughput. We just kept doing that all the way from 2 elements up to 64 elements, okay? And you can see from the numbers there, with 64 elements in this workload, we got about 144 million transactions per second. And the scalability, it's pretty much linear, okay? Now, let's be very honest here, you know, because of this, this is the extreme. This is about as good as it gets, okay? Most real-world applications won't get to this kind of level, but it shows what the technology is capable of, okay? We also ran the same thing, but taking out the updates. So just doing reads, and we actually got there to 1.2 billion selects per second sustained. Again, you know, this is the absolute high end. Real-world applications will be something less than this, okay? Which is why, of course, anyone who wanted to use this would, of course, conduct their own tests to see what performance they get with their application. But I have to show you something, right? I don't have them, so a couple of points about these numbers. These are using the GA release that came out in May. We have a patch coming in July that will push these numbers up by about 10 to 20%, okay? And we will also by then have some YCSB and sysbench numbers, which I can tell you are also actually very good, but we don't have those yet. They're still being worked on. So just to summarize, Scaleout, okay? Brand new feature, only been available since May. First release, so clearly a lot of extra stuff still to come over the next few years. But, you know, performance and scalability, especially for transactional applications, is the focus. A distributed database that doesn't appear like a distributed database. It looks like one database, okay? Full SQL, full ACID transactions, full consistency, automatic HA, elastic scalability, easy to use, easy to deploy, and, you know, on-premises or cloud deployment. It's great, isn't it? I want to just finish with a couple of things. So we did quite a lot of beta stuff last year. We had a beta program. We had a whole bunch of customers from various places around the world. Just a couple of quotes from some customers in the Far East that I was working with. So Samsung were very, very pleased. And China Mobile, who's already a big TimesTen user, are very excited about Scaleout. And I'm actually pleased to announce that now, 4 weeks after GA, we actually have a production customer. Yes, no one was more surprised than me. So this is China Mobile. It's the Chongqing Mobile subsidiary, and it's basically, it's a marketing promotion system, the thing we all hate, right? It gets all the location data from where you are and combines it with your profile and everything else, and then annoys you with promotional SMS messages and emails and things like that, right? They were already running this on TimesTen Classic 11.2.2, and it was working pretty well, but they were loading on more and more functionality, and they were starting to run into some concurrency issues, and just the capacity of a single HA pair just wasn't enough. So they migrated across with 0 code changes to the application. They just swung the application around, ran unchanged against TimesTen, and now they've got all their location-based services running without any problems at all, and they're very confident that they can scale in the future. So, coming to the end here, I hope you found that interesting. If you want to know more, obviously you can go to the main OTN portal where you can download the software, get a load of information, blah, 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 blah. Something that's quite nice, I've produced, and it's now available there, a VirtualBox-based VM, which contains a complete pre-configured scale-out instance. You can get it. It's got a hands-on lab in it. You can play around with stuff. And obviously, it's only a little VM. You're not going to get fabulous performance out of it, but in terms of functionality and experimentation, you can play around with it there. We've now got a GitHub area which has all our quick start and some scale-out specific sample programs on that, so you can go and check that stuff out and look at the code and play around with that, and I'm responsible, sadly, for most of that, so if you think the coding is terrible, that's my fault. And obviously, if you want to, you can contact me or your regular Oracle representative. And I guess this is the point where we say we've got about 3 minutes to take any questions. Yes, sir. Yeah. So it is exactly 2-phase commit, and in this iteration, it's synchronous. Everything is synchronous, right? That's why most of the numbers show k equals 2. In fact, in the very first GA release, we only support k equals 2, but again, we've got a patch set coming out towards the end of the year, which will take that up to k equals 5. As you increase the k factor, writes go slower. I don't have numbers yet, but for sure, we know they go slower. And you know, there's some things we can do to mitigate some of that, but no, if you increase the k factor, writes will go significantly slower. Yeah. That was k equals 2. Yeah, yeah, yeah. I mean, we do a lot of stuff. So our persistence mechanism, for example, by default, we don't synchronously write to disk. Okay, we have an epoch-based recovery system with k equals 2, which means we don't have to synchronously write to disk for the transaction logs. Okay. So that helps to, you know, we're not quite so bound by storage as we would otherwise be. You can run us with full durability, but things go slower, right? So. Sorry, have I considered? Yeah, we've looked at a lot of things. We're sort of thinking about some of those things for the future, maybe. We actually have some ideas of our own, actually, which we might do instead of those. So, you know, we've been working on this for 5 years. We've got another 15 years worth of work to do on this thing, right? I mean, these things are hard, right? I mean, I'm impressed that after 5 years, we've got this, right? So, you know, but for sure, there's a million things, you know, our to-do list is immense, Paul will tell you, right? So, yeah. So I think watch this space is the answer, right, for the next few years. Not today. We don't have any compression today, but again, it's something we're looking at. I mean, compression is a tricky thing, right? And it certainly affects performance, right? Same as encryption, right? You know, it's becoming almost essential to have encryption today. That's very much on our list, but that's going to have some impact on performance as well. So these are all things that will become in columnar storage. We actually have an implementation, but it's not enabled currently. So at some point, we'll turn on our columnar storage option as well. You know, there's a lot of things to come. But, you know, let's focus on what we have today, right? Yeah. Yes, so disaster recovery today, as of right now, we don't really have a very good DR story. We've got a HA story, not a very good DR story, okay? But that's being worked on, okay? We're looking at geo-replication if you want to have another grid in a different data center, okay? Ways to facilitate that, or maybe have one element in each replica set as an async remote copy, okay? So we're actually evaluating both of these options currently. What you can do in the cloud is you can split across availability domains, right? So you can put elements in different availability domains, but that's not really DR, right? That's just, a bit more safety. So that's a work in progress, basically. We haven't done a head-on comparison with grid gain, so I wouldn't like to try and make any comment on that, to be honest with you. I don't want to guess. We'd have to run the numbers, right? We've compared some other non-in-memory databases like Google Cloud and Aurora and stuff, and in our testing, we were much faster than those guys. Not only faster, but our latency was much better as well. But, we'll probably get to Aerospike in due course. How long it'll take us to do anything against grid gain, I don't know. I mean, it depends how many people are interested in seeing those numbers, right? Our performance team is only a few people. There's a limit to, how much they can do and how long it takes them to get through all this stuff, right? Because do a proper, benchmark which is reliable and honest takes quite a bit of time, right? Sorry, yes? Oracle's still selling coherence. I mean, coherence is different. That's an in-memory data grid, but it's not a database, right? It's very much a grid in the classic model where it's an object-based store. You can push processing into the grid. It doesn't have built-in persistence. It has to use external persistence. When we were first acquired, everyone was comparing TimesTen with coherence, even though they are completely different things, right? If I'm honest, we rarely see coherence now, and well, I've got to be careful what I say, but it doesn't seem to be so prevalent or so heavily promoted by Oracle any longer. I think so. I mean, they're very different beasts, right? I mean, if you've got a completely object-based application, you want to store objects, process them in a grid, and get them back, probably coherence is your choice, right? But if you have a relational application where you want to do transactions against a database, probably TimesTen might be your choice. We have to ship that stuff internally, right? So to keep everything in sync, right? Because PL/SQL has we have an SGA emulation inside TimesTen, right? Because TimesTen doesn't have an SGA, right? But PL/SQL uses that heavily. So we have to do it. We've done a lot of work to keep that stuff in sync everywhere, right? So, which, brings a cost, right? So I think we're about to be thrown out now. So I'll be outside for a while, so if anyone wants to come and ask me more questions. So, good afternoon, everyone. Welcome to the second afternoon of the European In-Memory Computing Summit, and welcome to my presentation here today. My name is Chris Jenkins. I've been working in the software industry about 36 years now.